All right, we're going to go ahead and finish up this section about point-slope form, and we're going to look at some application problems and our functions and using point-slope form for those problems. All right, so let's look at example 1. In example 1, we have in 1992, 1,250 students attended Eastside College. By 2007, the college had 1,425 students. Let C of T represent the number of students at the college T years after 1990. Okay, so let's go ahead and kind of break up this problem. The first thing that we have is we do have 2 points. So remember, we want to go ahead and label our 2 points. And one of the key things we want to remember is that T is the years after 1990. So in 1992, this is going to be year 2. This is 2 years after 1990. In that year, we had 1,250 students. What about 2007? This is going to be 17 years. This is going to be 17 years after 1990. And in that year, we had 1,425 students. Okay, so we have 2 points, and just like we saw in our last presentation, we want to find an equation that satisfies these 2 points. So our first step is to find our slope. So I'm going to let the second point, the 17, 14, 25, be my x2, x1. So if we subtract our y coordinates, we get 1425 minus 1250 over 17 minus 2. Okay, let's go ahead and simplify that. $14.25 minus $12.50 is $175 over 15. I think for this particular problem, as it does not divide evenly, I'm going to go ahead and use a decimal approximation. When I divide, I get 11.67. Now on your homework, make sure that you pay attention to what it wants, whether it be decimals or fractions, because you do want to make sure you report your answer the way that it wants it. Okay, from here, we do have a slope and we do have a point on our line. So let's go ahead and now plug into our point slope form. I'm going to use the first point, the 2,1250. And if we plug in, we get y minus 1250 equals 11.67 times x minus 2. Okay, so let's go ahead and work with this. Again, we want to go ahead and distribute. We get 11.67 times x minus 23.34. We can add 1250 to both sides. if we do that, we get 11.67x plus 1226.67. Now the last thing we want to do is we do want to be careful, because notice here I don't have the right variables. I should have C of t and t. So if you're going to use x's and y's in your computations and thing, that's fine. Just make sure that when you're done, you go back and you replace what you have with what you actually want. So for instance, on this one, we should have C of t equals 11.67 t plus 1226.67. This is now in function notation. Okay, so that takes care of part A. That's the hard part. So now let's go ahead and look at some of the easier parts. Okay, so we have our function. So for part B, we want to predict the number of students in 2010. So how many years after 1990 is 2010? That's going to be 20. So I want t equals 20. So if we plug that back into our function, we get C of 20 equals 11.67 times 20 plus 1226.67. If we go ahead and calculate this, 11.67 times 20 is 233.4. If we go ahead and add, I get 1,460.07. So I'm going to go ahead and can you have 0.07 students? And the answer is no. So let's go ahead and round this to the nearest whole number. We get 1,460 students. All right, that takes care of part B. Example C, when will 1,600 students attend Eastside College? So notice this is not a time, this is a C value. So in order to solve this, we actually want to set this equal to 1,600. And solve for t. So the first thing I'm going to do is subtract. I get 373.33. And then let's divide by the 11.67. I get 31.99. let's just round that up to 32. Now again, we do want to take into account our application problem. Are we going to have 1,600 students in the year 32? The answer is no. So we do want to go ahead and take our time to calculate what year that is. Remember that this is the years after 1990. So I'm going to add 32 onto 1990. We should get 2022 for our final answer. So make sure that you pay attention when you're talking about these problems involving years after a certain year. You do need to do a little bit more computations in order to find what year something occurs. All right, that's our first example. Let's look at one more. Our second example, we have in 1985, the record for the 100-meter run at Eastside College was 12.3 seconds. In 2005, it was 12.1 seconds. We want to let R of t represent the record in the 100-meter run, and t is the number of years since 1985. So let's go ahead and come up with our points. Now, we got lots of numbers running around here, more than we should. Does 100-meter run have anything to do with solving this problem? And the answer is no. Not all numbers are going to pertain to our problem. So let's go ahead and list out our points. 1985, how many years since 1985 is 1985? That's going to be 0. In that year, our record was 12.3. All right, 2005. How many years after 1985 is 2005? That's going to be 20. And in that year, our record was 12.1. So again, we have 2 points. The first thing I can do is find my slope. So I'm going to subtract my y values, my 12.1 minus my 12.3 over my x values, 2 minus 0. And if we do that, we get negative 0.2 divided by 2. And if we divide, we get negative 0.1. And I messed up. Sorry, this should be 20. And if we make it a 20, this should be negative 0.01. I thought it was off a little bit there. Okay, now that we have the correct slope, negative 0.01. All right, so the last thing we want to do is, now that we have our slope and we got some points over there, we can go ahead and come up with an equation. Now, if you remember in the last presentation, I said make sure that you always analyze your points before you start jumping into point-slope form. If we look at these, the first point there is our y-intercept. So we don't need to do any work on this problem. We can use our slope-intercept form. If we plug into our slope-intercept form, we get negative 0.01 x plus, what is our y-intercept? It is 12.3. Am I done with the problem? And the answer is no. Remember that, what did it said? It said r of t and t. So I need to replace my variables. So I'm going to go ahead and rewrite this in function notation. We get r of t equals negative 0.01 t plus 12.3. Now we are done. All right, let's go on to part B. We want to use the function from part A to predict the record in 2010. So 2010, what year is that? I'm going to subtract off 1985, and we should get that this is equal to 25. That's going to be my t value. So now if we go ahead and plug it into our function, we get r of 25 equals negative 0.01. Remember, we replace all of our t values with 25. Negative 0.01 times 25 plus 12.3. All right, if we go ahead and simplify this, we get negative 0.25 plus 12.3. And when I simplify that, I get 12.05. We want to include our correct units, and our correct units are seconds. All right, last part. Let's find the year when the record will be 12.0 seconds. So this is the record. We want to know the year. So we're going to plug 12.0 into our r of t. We get 12.0 equals negative 0.01 t plus 12.3. All right, we subtract 12.3 from both sides. We get negative 0.3 equals negative 0.01 t. And now if we divide by negative 0.01, we should get 30 equals t. Now again, remember that this value, this is the years since 1985. So what we want to do is we want to take 1985, add 30 onto it, and we should get in 2015. Okay. The last thing I want to talk about is some domain of some basic functions. The two that we're going to look at, or that you will see in this section, is first off linear functions. Remember in the previous section I said the only equations, the only type of lines that are different, that are not functions, are going to be vertical lines. So if it is a linear function, our domain is always all real numbers. So examples of linear functions, anything that can be written in the form f of x equals mx plus b. So now I want to ask you a question. if we look at f of x equals 5x minus 4 over 3, is this a linear function? And the answer is yes. Technically, I can separate that 3. And now note that we have it in mx plus b form. So don't get thrown off by fractions. If there was something in the denominator other than a number, if you had variables down there, then that would make this problem a lot harder. But for this, if it's just a number in the denominator, it is still a linear equation. And as it is not just a linear equation, it is a linear function, and therefore its domain is all real numbers. The second type that you're going to see on the homework is absolute value functions. An absolute value function, remember absolute value has the vertical bars. We're not going to play around with absolute value functions much in this class. I think this is the only time it really comes up. But one thing to note is the domain of absolute value functions is also all real numbers. So for instance, f of x equals the absolute value of x minus 4. Our domain is still all real numbers. You can plug any number in for x and get an answer. We're only going to talk about domain. Range of absolute value functions, that's where we get into a little bit more computation, and we will not be responsible for that. We're just going to talk about domain. All right, that takes care of this section. We've got one more section to finish off this module, and so we will look at that next time. So now that you have this, go ahead and complete your homework. If you have any questions, please remember to contact me.